You may ask yourself, how does refrigeration work? A refrigerator is a heat pump that absorbs heat from a region at a temperature below that of the surroundings and rejects heat to the surroundings. When we talk about heat transfer between system and surroundings in chemical engineering, we denote it with a capital Q. When heat is released by the system to the surroundings, Q has a negative value. When heat is absorbed from the surroundings, Q has a positive value. In an ideal system that is perfectly insulated, the change in Q is zero, meaning no heat transfer between the system and the surroundings. We also want to know the amount of work that is done on or by the system. We denote work with a capital W. If work is done by the system on the surroundings, W is negative. If the surrounding does work on the system, work is positive. In an ideal system, the net work will be zero. When we use the Carnot cycle, we measure the effectiveness of the refrigeration system by a coefficient of performance omega. Omega is found by heat absorbed at the lower temperature divided by the net work. Omega ends up being omega equals T sub C over TH sub TC, where TC is the absorbed temperature and TH is the heat of rejection. Enthalpy is another thermodynamic term. When a system is mechanically reversible in a closed system at constant pressure, enthalpy is the amount of heat transfer in that system. The equation for enthalpy is H equals U plus PV, where U is the internal energy and P is pressure and V is volume. When it is at constant pressure, delta H equals Q. When the system is mechanically reversible, delta H equals the integral of Cp dt from T1 to T2, where Cp is the constant pressure heat capacity. The classic refrigeration cycle looks like this. Where from across the evaporator from stream 1 to stream 2, there is low pressure and low temperature, and liquid enters the evaporator. In the evaporator, the liquid absorbs heat at constant pressure and exits as a gas at relatively low temperature and low pressure. From stream 2 to stream 3, a gas at low temperature and low pressure enters the compressor, which operates at constant temperature, which is called an adiabatic process. The compressor requires work input, and a gas at high temperature and high pressure exits the compressor. From stream 3 to stream 4, a gas enters at high pressure and high temperature into the condenser, and the gas is condensed down to a liquid. The condenser then releases the heat to the environment, and a liquid at high temperature and high pressure exits the condenser. From stream 4 to stream 1, there is a release of pressure and cooling of the liquid at the throttle valve. The liquid goes back down to the original low temperature and low pressure that we started with. This pressure and temperature combination is such that the enthalpy is constant and the work and energy exchange terms are zero. This means that enthalpy, delta H, heat, Q, and work, W, are all equal to zero, and the system is mechanically reversible. There are a few challenges with refrigeration though. One of these challenges is that the changes in weather can affect how efficiently the refrigeration process can run. With these changes in weather, energy consumption can fluctuate. Places like Texas, which can be very warm in the summer, can require a higher energy consumption for the refrigeration process. This increase in energy consumption causes more greenhouse gases to be released into the environment, like CO2. According to one of our sources, refrigeration and stationary AC units accounted for over 600 million tons of consumption of CO2 in 2010. Refrigeration helps with storing food and transporting food. Developing countries do not have the infrastructure to be able to use this refrigeration process, which can lead to food shortages. If there is anything that goes wrong within the system, then a chemical like ammonia can be released into the environment, which can lead to a large negative impact on the surrounding areas.
We've heard about the traditional Carnot refrigeration cycle. Now let's discuss a cutting-edge development in refrigeration technology. Ice point technology differs from the traditional refrigeration in two key ways. Where the traditional refrigeration system introduces phase changes by means of controlling the system pressure, Ice Point utilizes a change in chemical composition to change the melting temperature of the system's fluid. The Ice Point mixture is added to ice in step 1 of the cycle, lowering its freezing point by 25 degrees Celsius and allowing the system to absorb much more heat than it would otherwise be able to absorb. The key to Ice Point's ability to lower the freezing point is an endothermic effect that requires a large amount of heat to overcome. This is balanced by ice's high latent heat of fusion. After the ice is melted, the Ice Point is filtered from the water before entering the ice maker, so it will freeze at the normal 1 degree centigrade. The ability of this cycle to remove large amounts of heat near room temperature omits the necessity of the cycle to utilize pressure changes to introduce phase changes in the fluid. A key benefit of removing changes in pressure from the system is that hazards associated with pressurized systems are also eliminated. There were 87 pressure-related accidents in France in the year 2016 related to the manufacturing industry. Eliminating the need for pressurized systems could eliminate all said accidents in any given year. Worldwide accident totals would be several times this amount. In addition to eliminating workplace accidents, companies will also be able to save money by reducing these accidents in the workplace and creating an overall non-hazardous process condition. Another key benefit of this system is that Ice Point has no global warming potential. As one can imagine, water, which is used in this cycle, does not contribute to atmospheric pollution. This cycle eliminates the need for molecules such as CFCs, HCFCs, Freon, and halogens that have long been used in commercial refrigeration. So, this cycle cuts down on pollution and safety concerns, but how does it affect the manufacturer's bottom line? Mentioned earlier was the fact that Ice Point is filtered from the water after melting. When Ice Point is added back into the process to the newly frozen ice, that amount can be varied. Varying this quantity will change the freezing point of the mixture, allowing engineers to easily program a control strategy to control the amount of heat removed from the system at any processing conditions. This leads to a large increase in overall efficiency of the system. How much more efficient? Lineage Logistics reported an increase in their coefficient of performance, discussed earlier, of 56%. According to one of our sources, a large food refrigeration system retailer in Nevada used about 2 billion kilowatt hours per year in refrigeration costs. According to our coefficient of performance, the Ice Point system should be able to increase the performance by 56%. According to the national average of 12 cents per kilowatt hour, this should come up to about a savings of $170,000 per year just for this one retailer. As chemical engineers, a new process such as this is incredibly important. In industry, the companies that succeed are those that can innovate. Learning the basics of a classical system like the Carnot cycle are a great beginning to our knowledge, but new technologies like Ice Point are examples of an ideal that we can all strive to achieve. Thanks for your attention throughout this video. Credits and sources will follow.